Hello, my name is Eamon. I'm a member of the Association for Computer Machinery and Upsilon Pi Epsilon International Honor Society for Computing and Information Systems. I study computer science and software engineering at the University of Washington, and this is a presentation on using the GPIO pins to run game controllers on the Raspberry Pi. The one I happened to use for this particular project was an Atari 2600, but the Sega Genesis and Sega Master System all are active low, short to ground, same style of controllers, so this method will work for those controllers as well. The only major change is for additional buttons on Master System controller, giving the additional pin settings in the program, and for the Genesis program, you need to have a 5-volt power in because some of the pins are multiplexed because there was an 8-button option, and the power in powers a CMOS that acts as a selector pin. So other than that, they're essentially the same though. And here we go. So this is a basic overview here. What do we need to do in order to get our game controller to work with our GPIO pins? Well, we need to be able to set some GPIO, general purpose input-output pins, as input or output. So because we need to be able to send and receive signals from the controller to monitor various state changes, such as is up pressed, is A pressed, is B pressed, which will be active low, which means when the current drops below threshold, it's logically false, it's a 0, it's active low. That's our second point here, checking the status of the GPIO pins. Basically, we need to monitor the state of the input or output pins that we've assigned to determine what particular state the controller is in, and so forth. And we need to be able to change the state of a pin. This is not necessarily for the particular controllers that I'll be discussing in this tutorial, but for example, the Nintendo Entertainment System and Super Nintendo Entertainment System controllers have a latch and a clock that needs to be artificially produced, because obviously 700 megahertz Raspberry Pi runs at a much different clock rate than the 24 or so megahertz of the Nintendo or Super Nintendo, or something to that effect. So you have to emulate the clock signal and also toggle the latch, so you have to be able to write out to pins in those. I don't do that in this particular tutorial, but that's something that you do need to do for some gaming controllers. And we need to be able to respond to the state of pins. We need to translate the state of the pins into a form of information which the computer can respond to with appropriate actions. So we need to monitor the state of the pins, and depending on whether the controller is active high, active low, or communicates serially like the Nintendo Entertainment System or the Super Nintendo Entertainment System, Super Famicom controllers do. That's slightly different, but we do need to still respond to the state of the pins. And now we'll get into how we do it. Setting the GPIO pins to input or output, we need to set the status bit of the pins and registers associated with each of the pins we want to assign. Associated with each of the 53 GPIO pins is a 32-bit register. Well, there are more than one pin per register, which I'll get into here in a minute, and we need to change the status of those particular bits, be they either 0 or 1, which is 0 logically false, 1 logically true, generally speaking. Those are the translations we'll use. This is an overview of the registers associated with the GPIO pins in the Raspberry Pi. As you can see, there are a lot of registers here. We're not going to be using all of them. We're going to be reviewing the GPIO function select registers first, and some of these other registers can be used to detect events and trigger interrupts and so forth. But if you're going through the Linux kernel, you can't really trigger a user level interrupt with the GPIO pin, unfortunately. Not that I've been able to figure out how to do anyway. So you'll probably end up using polling. So we're going to use the GPIO function select registers to set our pins to input or output. The high order 2 bits, that is the uppermost bits of the 32-bit registers, are unused. So we have a total of 30 bits, that's bits 0 to 29, divided into groups of 3 bits. Each group of 3 bits represents 1 pin, and therefore there are 10 GPIO pins per 32-bit register. And we set these bits to determine the states. So in GPIO function select register 1, bit 0 through 2 If we set those to 0, 0, 0, pin 0 is an input. If we set those to 0, 0, 1, pin 0 is an output. Going to GPIO function select register number 1, if we were to set these bits 0 through 2 to 0, 0, 1, pin 10 is an output because pins 0 to 9 are found in GPIO function select 1, and so on and so forth until we get to the last register here where we have pins 50 to 53, so obviously we're not going to use all of the pins in this particular register, so keep that in mind if you're writing to register 5. Don't overwrite weird bits that aren't assigned to you because you don't know what can happen, and you can do this with a simple bitwise operands, which are available in any programming language, pretty much any good object-oriented programming language, Python, Java, C++, etc. And this is just an overview of what the register looks like. The GPIO function select register, the 000 input, 001 is an output, and a lot of the GPIO pins have an alternate functionality, like some of them can be set up to be universal asynchronous receiver transmitters, UARTs for short, or they can be set up to be PWMs to send waves and so forth, so you can use those to emulate clock signals and things like that. But we won't be doing that in this particular tutorial, though. So how do we check the status of certain GPIO pins? So we'll want to know whether the level is high, whether the level is low, depending on what state we want to respond to. High being generally, we'll see that as logically true in electrical terms. That would mean the threshold voltage going to your GPIO pin is above the threshold voltage, whatever that may happen to be, or low, 0 false, which is below the threshold voltage, which is our controllers, the Sega Genesis, Master System, and the Atari controllers are all active low, so we'll be monitoring, looking for a low state. And we get that value by reading the bits stored in the the pin level register, essentially, is what it's called here. And I'll give you an overview here of that. There's a direct one-to-one relationship between the pins and bits of the GPIO level registers. And there are only 2 of them because there's a direct one-to-one relationship. And we use all of the bits in these 32-bit registers, unlike our GPIO function select registers, which didn't use the high order bits, the high order 2 bits. So GPIO level registers, 0 represents the state of pins 0 to 31. So bit 0 represents pin 0, bit 31 represents pin 31, and so forth. And the GPIO level register 1 represents the state of pins 32 to 53. And we don't use the high order 10 bits since we're only representing these GPIO pins here. If a bit is 1, the pin is high, and if the bit is 0, the pin is low, which we discussed high and low states earlier. So we'll need to read in the values from these registers, and a simple way to do it is just use a bitwise AND, or whatever your bitwise operation of choice is, and get rid of the bits you're not interested in and check the state of the bit you are interested in, and that will tell you whether the pin is high or low. And this is one of the misprints here in the BCM2835 ARM technical manual. It says if it's 0, it's low, and if it's 0, it's high, which obviously isn't true. If it's 1, it's high. If it's 0, it's low. And there's some typos like that here and there throughout the manual, but nothing too major to overcome, because obviously 0 generally is low. So testing has confirmed that. Now respond to the state of the pins. How do we respond to the state of the pins? In my case, I use the Linux uinput and input headers to create a virtual device and inject relative access, those are mouse events, and or keystroke events when the desired pin state occurs. And this is a note about the register mapping that I showed you earlier with the GPIO registers. It shows the address begins with a 7 in the high order hexadecimal bit, followed by an E and a 2, but this is not the physical address. This is the virtual GPIO base address. So the physical GPIO base address, which you'll need to use when you're manipulating pointers and so forth, is actually 4 in the high order hex bit of the 32-bit address here. And there are some potential pitfalls to discuss here. The memory mapping via the Linux kernel must be completed with root privileges. In other words, whatever you compile that creates the driver for your controller has to be done with sudo or similar privileges. The same applies for memset. You need root privileges for that, and even in higher level language abstractions like the Python library, you probably won't see this going on. You won't see the memset, you won't see the memory mapping the Linux kernel, but it is going on behind the scenes. So your Python script does need to be executed with root privileges as well. And in the event you're creating your own pointers, you want to use a volatile pointer to the memory map to prevent the pointer from being simply cached by the compiler, because we need to check that to make sure it's still valid. And we always want to use key syn after key press and release, and this is one of the things I'm complaining about. Open source is great because you can look at the code and it's fun to work with and you can contribute and all of that, but some of the documentation sometimes is not fantastic, and finding documentation about the Linux uinput header was not particularly easy, and for the longest time I was using key press and key rel thinking it was key release, and getting a lot of very strange errors, and it turns out you just inject key press 1, then you inject key press 0, then you synchronize them by injecting key synchronize, and that causes event key press, event key release, which gets you the proper behavior. So don't think that key rel is key release. It's relative access events, and that's what we use to create mouse events such as this. Ooh, relative access event. And you always want to check for a valid file descriptor and return values from your Linux functions that you'll be using for memory mapping and so forth. File descriptors, of course, being part of the system that Linux uses to communicate back and forth and so forth, and you can use that in more advanced settings through pipes and dupes to communicate via threaded processes and so forth, but we won't be doing that for the purposes of this demonstration. And you want to check errno and call p-error in the event of failure to track down these elusive errors, which goes along with this here. You want to set p-error and print to c error, and always read your messages and figure out what is going on, because some funky things can happen when you're working with file descriptors and the input-output libraries trying to inject key events and create virtual devices and so forth. And these are some cautions I thought I should review. Whenever you're messing around with the GPIO pins, you need to remember they're not 5-volt tolerant. A lot of pinouts will erroneously tell you that the Atari controller or the Sega Master System controller has to have 5 volts, when in fact it doesn't. It will work fine off 3.3 volts. The Genesis controller does need the 5-volt in, but otherwise the rest of it will be fine on 3.3 volts. So you always need to make sure that you're doing something to reduce the voltage of the 5-volt pin below 3.3 volts, because if you try and put 5 volts onto a 3.3 volt GPIO pin, you'll probably destroy your computer, because there's no protection for your GPIO pins. Probably a cost-saving measure on their part. So be very careful there, obviously. Always connect your ground wire, so don't hook up a circuit without hooking up your ground wire. That's very important. Ground yourself before touching the Pi, or get a good anti-static wristband. Ground yourself would be touching something metal or something, but I would just get the anti-static wrist strap. It's a lot safer, easier, don't have to worry about it, they're cheap. And you want to make sure you understand the different GPIO numbering schemes before assigning any pins. There's the logical view, which is your view, 1, 2, 3, 4, and so forth. The BCM, which is the processor's view, which is not logical, meaning it doesn't count top to bottom, 1 to 2, 3, 4, etc. It jumps around a little bit, but that's the logical view that your processor on your board sees. And there are other custom views, such as the wiring pi scheme, which is good header if you're not a really advanced programmer as well. So you don't want to accidentally reassign GPIO pins that are meant for other vital system processes. So you want to make sure you understand what's going on here, and possibly have a good backup of your system in case you mess something up when you're messing around with a startup script or so forth. I'm going to review some of the software tools you can use to do this. You can use Python. The rpi.gpio library provides an easy-to-use high-level abstraction of accessing the registers I discussed earlier, and there's other GPIO functionality that you can do, such as setting pins and so forth, which we discussed you might need for the Super Nintendo Entertainment System or the Nintendo Entertainment System controllers, because they have embedded computers that you need to communicate with. And it also has a good high-level abstraction of the U input library, which is actually very difficult to work with if you don't know what you're doing. But the downside is it's really simple. Not much programming skill is needed. It's kind of plug and play, and it's a dynamically typed language, so it's not very efficient. Meaning it doesn't bind and type to things at compile time. It's statically. It does it at runtime. So there's a lot happening at runtime, and also it's dynamically typed, meaning it doesn't reserve a small portion of memory like C or C++ does. They reserve memory for a Python object, which is not efficient, and it's not the most appropriate choice for embedded systems because you have limited resources relative to your typical desktop computer, so you want to try and use a programming language that's efficient with respect to memory and processor usage, and Python just isn't that language. Wiring pi.h is Gordon's header, which is great. It's easy to use. I used it before I wrote my own library. Leverages the Linux kernel and does some simple echoes and exports and so forth through the command line, and does all the stuff you need it to do very simply. And it's a C program, so there's a dynamic typing or other stuff with Python, so there aren't efficiency concerns. The downside is you don't learn a real lot by using this high-level abstraction because you're not really interacting with pointers and the registers and so forth. So you don't need a lot of skill to do it, and you don't learn a lot, but you are using a more efficient language, and it's a good library to begin with. And if you're not familiar with the platform, it's a great place to start to just test your logic and your functionality of your program, and then add your own more efficient functionality as you go along. Also, there's no high-level abstraction of Linux U input here, which is rough because it's hard to work with. And there's the BCM2835 header, which is Broadcom's supply library, the makers of the ARM process. It's a slightly higher level abstraction of the register manipulation. So rather than creating pointers to registers and manipulating them with bitwise operations, you're using methods contained in their class. But I did not like this library at all. The documentation isn't easy to understand. It's not particularly thorough. The methods require obscure data types as parameters, UNTI, weird stuff. They're difficult to use. The logic they use to manipulate the registers doesn't necessarily follow the way I would logically do things, so it's kind of difficult to wrap your head around, and they don't do much to simplify the interactions with the GPIO registers. You spend a lot of effort to learn how to use these complicated methods with weird arguments, and then there isn't a lot of takeaway. There isn't really anything here that you can apply to other programs and so forth. So I didn't enjoy the library. I took a look at it and didn't end up using it. And there's no high-level abstraction of Linux U input either, so it wasn't helpful in that respect. And you can also write your own C++ solution, which is what I did. There's no high-level abstractions of Linux U input or the GPIO register interactions. However, you'll learn a lot about using bitwise operations, memory maps, file descriptors, pointers, Linux permissions, and various Linux features by writing your own code. You'll also be able to understand every line of code in the program, which is nice to be able to look at a code and read it and know what it does, and you'll have a lot of takeaways from this, and it's fun once you get the program running. And I'll be reviewing the details of my software implementation in a later tutorial video, and I'll probably be putting it up on GitHub here shortly for you to manipulate. It's not completely finished because that would be a little too easy, but some of the basic functionality is implemented, and you should be able to poke around the comments and more or less figure out how to implement any additional functionality that you happen to want to add. And that is the end of the tutorial. Thank you for listening.